Hello, with apologies for, um, you know, dumping a bunch of technical stuff on you at the end of the course. Um, uh, I just want to wrap up in this podcast the rest of the discussion on orbits, and I'll do one other quick podcast for which actually slides are almost not necessary, with a couple of philosophical thoughts on reliability. Um, we already started the orbit, so let me go directly to. I wanted to do the rest of it, and I stopped where I stopped because I've been talking pretty much, in general, and I wanted to make a couple of specific points about how we talk about orbits. If you go to slide 26, it says more circles, ellipses, and beyond. The key to that slide, there's a couple interesting things on that slide. One is, if you think about a satellite, this is in the case of the Earth, in sort of a generalized orbit around the Earth, how would we describe it? And, if you want to go back to sort of the real basics of how do you describe a body moving in three-dimensional motion, you can do it with 6 numbers: x, y, z, its position, and the x dot, y dot, z dot, its velocity vector. Because if you define those two things, you've defined, the orbit. If you put an object at a certain distance from the Earth and then you tell me which way it's going, there's only going to be one orbital path that is going to be solvable for that. So in a way, if we could measure those things very easily, and nowadays we probably could measure those things pretty easily, at least for some orbits, where we might have a GPS signal, which is not really all that many of them, but in low Earth orbit, we would know x, y, z, x dot, y dot, z dot, but that historically, of course, is not how we define ellipses. It's not a very intuitive or geometric way of describing an ellipse, not that the way orbital people did it is either. But you'll always hear, about the line elements, the 6 line elements. There's always 6 orbital elements because in three-dimensional motion, you can fully describe it with 6 numbers because you have 3 position and 3 velocity. And in a way, you could think about it like the velocity defines the energy. And so that defines, how big the orbit in a Keplerian sense, how much area it's going to be sweeping out. So the 6 orbit elements that we are normally talking about, I listed on this page in green. And to tell you the truth, I don't think you really need to know this, but you'll run into it. And so you just like to kind of know what do these words mean. And so I'm just going to explain what they mean. Normally we use one number up for the eccentricity of the ellipse, which would be a number like 1 if you're in a circular orbit, or it would be a number like 2 if your highest point was twice the altitude of your lowest point measured from the center of the Earth. You consider the Earth to be sort of a point mass. Okay, so that tells you the shape of the ellipse. It doesn't tell you what the altitude of the ellipse is, so that takes up a second number. How big, how high is the perigee or how high is the apogee? So now you pretty much have the ellipse totally described. But what you don't, there's several things you don't know about that ellipse. One is, what's its angle relative to the equator? It could be a polar orbit, and it could be an equatorial orbit, or it could be a 45-degree orbit, or anything in between. So every orbit has an inclination. And then, how is that plane oriented around the Earth? You could, let's say you've got this elliptical orbit passing through the center of the Earth. There's 360 degrees you could clock it around. So we tend to measure that by what's the angle we could have defined it as what's the angle relative to longitude where it crosses the equator. So does it cross the equator going up toward the north, under New York or under London, or tell me what that's like. The trouble is, since the Earth is spinning, that's very inconvenient because you'd have to say, well, what time of day, when it crossed the equator, which time? Because every time it crosses the equator, it will be under a different part of the Earth. So that's not very useful. So what we use instead is we use a vector to the sun on one particular day, which is the spring equinox. That defines a vector in space, and then we say, okay, what's the plane where does that plane cross the equator on that day relative to that angle? So it could cross the equator right opposite to the sun, or on the exactly on the sun side, where that vector is that leads from the Earth, center of the Earth, to the sun on March 21st, or it could be any angle from there. So that's the longitude of the ascending node, which is kind of a fairly confusing way to say it. And so I wrote versus the equinox, versus the line to the sun on the 21st of March. And then, where is the perigee and where's the apogee? You could basically rotate that ellipse. You've got the plane totally described, the plane of the orbit. You haven't told me where the perigee of the ellipse is relative, or where the apogee of the ellipse is relative to that crossing point. So there's one more rotational thing, because that ellipse could be rotated around inside the plane, and that gives you 4 numbers. Then you need to know where is the satellite at any time t0, so that I can get the clock started. Where is the satellite at noon on Friday? If I tell you where the satellite is on noon on Friday, now you know everything, because that orbit will have a certain period. You can propagate it forward with an orbit propagating piece of software that'll tell you how long it takes to go around that orbit, what the orbit period is. And so if I know what the orbit period is, and I knew where it was at 4 o'clock on Friday afternoon, then I know where it is, at all other times. So we need one fixed point. And that fixed point is usually the time where some certain angle is 0. So maybe the time when it goes through perigee, or maybe the time when it goes through apogee. We call that the epoch. Where's the satellite at time t, or what time is it when the satellite reaches a certain point? And different standards use different ways of talking about that. Okay, so those are the 6 orbit elements. I went through all that just to say, look, there are 6 numbers, and these happen to be the 6 numbers that they are. They're not going to be that meaningful to you, but the software that you use to propagate orbits is always going to ask you for those 6 numbers. When Air Force Space Command, or now the Space Command, is tracking your satellite, that's what they're going to give you, those 6 numbers. And so then all of the orbit tracking software that you buy is compatible with those numbers. And I have to say, I've never done this. Mr. Rick, the guy who calculates everything rough by hand with an Excel spreadsheet, has never done that for an orbit. So, it's not something that, that we do very often, but at one time, of course, people did calculate all these orbits and do lots and lots of calculations to figure out what orbit something was in based on, observations of pieces of the puzzle. So I did a slide, which I think was kind of interesting, on slide number 26, talking about going around an asteroid. And the reason I like this slide is that it includes in it some equations which are kind of standard equations for what's the velocity that you need to be in a circular orbit. It's the gravitational constant divided by the radius taken to the square root. Okay, and what's the escape velocity? It's 2 times the gravitational constant divided by the radius taken to the square root. So that's twice the circular orbit. So if we're 7 kilometers a second in low Earth orbit, it's 14 kilometers a second to totally escape from Earth's velocity, so that you would leave on this, on this trajectory where the Earth is pulling you back, but you have enough velocity that when you get to infinite distance from the Earth, you're at 0 velocity. So you just barely escape. That's the minimum escape energy. So I use those equations, and the last one is the period of the orbit. What's the period of the orbit? So, and there's a similar equation for that, r cubed divided by the gravitational constant, the square root of that, times 2 pi. So I did all these calculations for an asteroid, which has this, gravitational constant much, much less than the Earth, 10 to the 11th times less than the Earth. Okay, it has a radius 1,000 times less than the Earth. So the gravitational constant divided by the radius is 10 to the 8th, 100 million times less than the Earth. So orbiting around an asteroid is very tough because that ratio is so small. So the circular velocity, the speed that you have to go to be in orbit around an asteroid, is 10,000 times less. So it's very, very slow. If you want to be in orbit around an asteroid, you have to go very slow because its gravity is very weak, so your centripetal acceleration has to be very, very low. The little string, that's holding you in orbit around is a very tenuous string, so you just go very, very slowly to balance out, your tendency to go in a straight line and the tendency of gravity to draw you back into the asteroid. So instead of 7 kilometers a second to be in orbit around a small asteroid, 50-kilometer asteroid, you're going to be going 0.7 of a meters per second, 1.4 miles per hour, which is, reasonably slow, a couple of kilometers an hour. And, v-escape is like 2 miles an hour, which means if you were on an asteroid and you jumped into the air, you would never come back. So, but in a way it makes sense. How much gravity does a little rock like that, really exert? Not much. And what about the orbit period? That's an interesting question because the orbit is smaller, obviously, because the diameter of the asteroid is much smaller. But so you have a much shorter path to go around. But on the other hand, you have to go much slower, and it turns out it's longer. As gravity is weaker, the orbital period is longer. And you can see that in the Earth. A geosynchronous satellite is where gravity is weaker, out there at 39,000 kilometers from the Earth's center. So, out there, its period is like 24 hours, a little less than 24 hours. Whereas when we're close to the Earth and the gravitational is stronger, we have to be going faster. And so our orbital period is like 97 minutes. So, those two slides are kind of, okay, these are, the way the calculations get done. Then on slide 28, I restated the orbit elements. And then I listed again, obviously this is an area that was always very confusing to me. I listed again in orange what the 6 classical orbit elements are. 3 elements that describe, the conic, and 3 that describe the orbital plane itself. 3 that describe the shape of the orbit, how big it is, and how big it is in terms of how many kilometers is the apogee. And then what's the eccentricity, and then what is the angle between, where are we? Where are we on that orbit? How many degrees around the orbit have we gone, where 0 is the perigee in this case, which is the easiest, way to go. So then there's the Y6 orbit elements, which I already covered. Then, some orbit facts. These are, things that a lot of people forget. And one is that you can only be synchronized with the Earth at the equator. As we talked about, if you're not at the equator, you're going to be going north and south of the equator because the orbit plane has to pass through the center of the Earth. The Earth's gravity is radial, passing through a point in the center of the Earth. So you can't be, in a plane that doesn't cross through the center of the Earth. If you were just in some random plane that, were above the North Pole, parallel to the equator, you would just fall into the equator because you don't have an acceleration to overcome the force of gravity that's drawing you down from the North Pole toward the center of the Earth. So every orbit is in plane, and that plane has to cross the center of gravity of the thing you're going around. And if you're in geosynchronous, if you have a geosynchronous period of 2355, but you're in an inclined orbit, you won't always be over the equator. Sometimes you'll be north of the equator, sometimes south of the equator. And, I made this drawing where, to show what a sun-synchronous orbit is like. I made the drawing on the right, which is really pretty amazing. It shows the orbit so that the orbit is always in the dawn-dusk line. That would be a sun-synchronous orbit. And the question is, how do they do this? Because obviously that orbit plane is rotating 90 degrees. Orbit planes on their own do not rotate. Normally a satellite If it were in dawn-dusk orbit on the right, by the time the Earth went 90 degrees around the sun, it would be in a noon-midnight orbit. And then it would be in a dawn-dusk orbit on the other side, and then noon-midnight orbit again as the Earth went around the sun. So there's a trick to flying in a dawn-dusk orbit, and that trick is shown on slide 36. Orbital trick number 3, sun synchronous. They're just very lucky fact about the Earth is that it's not actually round. It's much thicker at the middle, probably because it's been spinning around its axis for so many billions of years, and it's not really solid. So it's slowly, getting wider in the middle. And so when you go over, let's say, Moscow, you actually are not entirely being drawn into the center of the Earth. There's a component of the Earth's gravity that's pulling you toward the equator. And if you think of your spacecraft as a gyroscope, and you push on the gyroscope, pushing it toward the equator, you're going to rotate the plane of the gyroscope in the direction 90 degrees advanced of your orbit. So that is going to push the plane of the orbit around. So what you have to do, imagine if you were at an infinite distance of the Earth, it would look like a point, and that effect would not exist. If you're in very low Earth orbit, the Earth looks highly oblate to you because you can see all the details. So the effect of that torque, of that asymmetric torque that you get from the Earth that pulls you toward the equator when you're north and up toward the equator when you're south, and tends to rotate the plane of the orbit, gets stronger and stronger and stronger as your inclination gets higher, so that, if you were in equatorial orbit, you'd never notice a torque, because the Earth looks symmetric to you from that orbit. And if you're in a 90-degree orbit, it also looks symmetric to you. But if you're inclined a little bit, if you're at an 80-degree orbit, you're going to be feeling that pull to go to the wide part of the Earth. You're not going to be feeling entirely just a pull to go to the center. And so, unfortunately, if you go to an 80-degree orbit, it pulls you the wrong way. You have to go to beyond 90 degrees, and typically that number is like 96, 97, 98 degrees, will give you, depending on the altitude you're at, okay, for that reason, go to slide number 37. I made a little chart here. How much is the perturbation? And how much does that, as a function of orbit inclination? So if you look at orbit inclinations where they are, at 90 degrees, it crosses through 0. So, but if I get a little bit off of 90 degrees, I can get orbit inclinations that are precession rates in degrees per day. You can see the numbers on the left-hand side. I'm sorry, it's not, it's not the clearest, chart I guess I could have made. Just trying to blow it up so I can read the numbers myself a little bit, because they are a little bit hard for me to read too. So you just have to blow it up. Okay, now I'm seeing them fine. You need a precession rate of 1 degree per day to make this happen. And so if you look at the inclination, and it has to be positive, you want to be at an inclination that's like 100 degrees. That inclination is going to have to be bigger, depending if you're at a 100-kilometer orbit, the effect is much stronger. So it will be adequate to be in 95 degrees or 94 degrees. If you're at a 2,000-kilometer orbit, the effect is going to be weaker. And to make a long story short, that's what we do. We launch satellites into very precise inclinations, as if it were going around the equator from west to east. And then you inclined it 90 degrees, and then you inclined it 3 or 4 or 5 or 6 or 7 more degrees. The extra pole, what I wrote down as extra pole, will precess that plane around 1 degree per day. So it's kind of a kludge, if you want to think of it that way. I mean, it's kind of a kludge. And what that means is it's just taking advantage of this freaky, effect of the Earth being, not totally a sphere. And that means there's no, kind of like physics equilibrium point. You reach that point, no, I'm always pointing at the sun. No, it's just the orbit doesn't know that you're going around the sun once a year. All it knows is the Earth is not symmetric, and it's slightly off from being in a true polar orbit, so it sees that asymmetry that pulls it toward the equator, when otherwise it would just be at a normal apogee. And so that causes the plane of rotation to change. You have to adjust, modulate the altitude or the inclination to maintain that coincidence of exactly 1 degree per day. It's not easy. I've done a lot of calculations, with, okay, how much error can I have in the inclination and the altitude and stay sun synchronous for a year? And it turns out it has to be super, super precise, and most launch vehicles will not guarantee that to you. So every sun synchronous satellite has a propulsion system on it to either change the inclination, 95.1, 95.2, they actively do that, or lower and raise the altitude to get a stronger or weaker effect. Everybody talks about, sorry to burn up so much time on it, but everybody talks about sun synchronous orbit like it's some sort of magic slot you drop into. No. It's the balance between different forces, and it just so happens to result in a 1 degree per, the users think, oh, there's nothing to it. You just, the reconnaissance people like 10 a.m., 10 p.m. orbits. So because they have a reliable shadow length, and they know what time of day it is when they look down on the ground, oh, it's 10 o'clock in the morning and therefore the sun, et cetera, et cetera. It's nice because you also get the same color temperature every day. It's a nice repeatable thing if you're taking pictures with a camera of the Earth to always have the same sun angle for various reasons. Length of shadows, coloring, if you're trying to get crop health and things like that. And obviously the outside world doesn't stop to think, how did they do that? We're the guys who have to stop and think, how are we going to ever do that? And it does require, propulsion and watching the orbit and seeing how, the time of day that it crosses the equator is changing from day to day and adjusting the orbit to keep it synchronous with the sun. Okay, there's a very basic concept on slide, sorry to jump around, but trying to put it in some sort of, order that I can do it quickly. How do you do an orbit transfer? How do you get from one orbit to another? And the simplest case of this is on slide 32, going from the green circle to the red circle. You're in low Earth orbit, you want to go to geosynchronous orbit. How do you do that? The rule of thumb, because the satellite's orbit is defined by x, y, z, x dot, y dot, z dot, you want to find a linking orbit, an orbit that at one point has the same x, y, z as the orbit you're starting off in, like you got dropped off in low Earth orbit, but has enough velocity, x dot, y dot, z dot, that it will actually be an elliptical orbit that touches, that kisses the new orbit that you want to be in. So for the Hohmann transfer, what you need to do, you want to get to that golden orbit, the yellow or golden orbit. And the way you do that is you give yourself excess velocity when you're at that, what would now become the perigee point. Therefore, you look like you could say hi to your friend who's in low Earth orbit, and you're both at the same point in space, but you're not in the same orbit because you are going way too fast. And all of that excess velocity on the other side of the orbit, 180 degrees away, will translate into excess altitude. Okay, so you're like a child on a swing, two children on a swing. They cross each other. They are parallel to each other together when the swing is at the bottom. But you're going much faster, so you are going to swing much higher. Okay, so when you get to that point much higher, you could shake hands with your friend who's in geosynchronous orbit. Oh, I'm in the same orbit as you are, but you're not. Because you're going too slow and you're going to fall back down. You're in an elliptical orbit. You don't have as much energy as the geosynchronous guy. You need more energy. You're going too slow at the apogee because the Earth's gravity has exchanged that excess velocity you used to have for excess altitude, so you don't have much velocity anymore. You're going slowly. Okay, you can fix that. More propulsion. Give yourself another kick, another velocity increment, and that's why we call it delta V. How much too slow are you going? Oh, I'm going 1,000 meters per second, too slow. Okay, rocket engine, give me 1,000 meters per second of acceleration, and I will be in geosynchronous orbit. Fantastic. So that's how you do it. 2 velocity kicks. One to get you into the ellipse that joins the first orbit and the second, and the third orbit. And then you're in the second orbit. We call that a transfer orbit. So that transfer orbit could be between Earth's orbit and an orbit around some other thing like the sun. So you could put yourself in orbit around a lot of different things. Another way to do it is you could be in low Earth orbit and you want to be in the same orbit as the space station because you want to dock with the space station. So you put yourself in an orbit that's a little bit below the space station, right? Then you give yourself a little bit of a kick so that your apogee is at the same altitude as the space station, and then wait until the space station and you happen to go by each other. Okay, every orbit it's going to be a little different because your orbit period is not the same as the space station. When you guys are close, give yourself a new kick and you're now in the orbit of the space station. So that basic Hohmann transfer idea is at the core of every orbit transfer. I mean, Earth is in a certain orbit around the sun, and Venus is in a certain orbit around the sun. It's just that Venus' orbit is lower. So you would need, basically, Earth is in the red orbit and Venus is in the green orbit. How do I get from the red to the green orbit? You know, so, I mean, in terms of orbit around the sun, you're not orbiting around the Earth. So all of these transfers have the basic same thing. And the same thing is true. And the reason I have the three arrows, the red arrow, the green arrow, and the yellow arrow, let's say I'm in equatorial orbit and I want to be in a 28-degree orbit. I need to give myself a velocity vector to turn that red vector 28 degrees. That's a classic geometry problem. So I've got an internal angle of 28 degrees, and I've got a length of that red vector, and you can solve for the length of the green vector to close that triangle. And because in Earth orbit that velocity is super high, like 7-point-something kilometers a second, if you want to make a significant change, like a 30-degree change, you're talking thousands of meters per second. So we mostly don't do that. The planes, we can change the plane of an orbit a tenth of a degree or something like that, but making a plane change of like 30 degrees is a very big deal. Making an altitude change is actually much less of a deal as long as you stay in the same plane. So that's how we basically launch satellites into geosynchronous orbit. We put them in low Earth orbit at the equator, and then we do two Hohmann transfers. Many times the launch vehicle has already done the first Hohmann transfer. It depends on the launch vehicle. The Russians go directly into GEO. Other rockets put you into the elliptical orbit. Other rockets put you into the low Earth orbit circular, and you have to go from there. This famous mission that I worked on in the 80s, I think it was 1983, where we were launching a geosynchronous satellite and it was nearly lost in space. It was launched on the space shuttle, and it was brought to a low Earth orbit. And after that, there was something called the inertial upper stage, which was a big hydrogen-oxygen rocket stage. And that was supposed to raise the orbit into the transfer orbit and then do another raising to circularize it in GEO. And in that first burn, it pretty much got the satellite part of the way into the yellow orbit. And then, it was when they say that these satellites are lost, they're not really lost, but they don't have the propulsion to get to the orbit. We know where they are. They're not lost. But they're lost in the sense that we cannot get them to the orbit they want to be at. That particular satellite had a lot of propulsion for holding it in the target orbit, for maintaining it in geosynchronous for 17 years. And it even had a little bit more propellant by accident because some other payload dropped out of that launch, and they needed somebody to put more mass in, and we filled the tank to an even greater amount. We had extra tank capacity. So by complete accident of fate, we had hundreds of kilograms of excess hydrazine on board, which we thought at the time, well, they need the extra mass, maybe we'll get extra lifetime on orbit. And we used our onboard propulsion system, the attitude control and orbit trim system, to do that transfer. So it doesn't have to be done in one gigantic burn of a rocket. You can do it in many small burns of small rockets. And the interesting thing about that is you can then think about doing electropropulsion where you have very, very low thrust, very efficient, but very low thrust, but over the course of 3 months, you can make the transfer. So, okay, if you go to a slide like slide 38, this slide always confused me tremendously. These are the plots you see of the orbit, and you think, how could the orbit be that complicated? It isn't that complicated. It's just crazy to plot an orbit on a Cartesian map of the Earth, because the orbit is all about the Earth being a sphere. And so for that reason, the orbits look very peculiar, because what they're trying to show you is that it goes over the South Pole and over the North Pole in some sense. But what you can see from this orbit is that you have a bunch of parallel lines, yellow lines, that are descending, right? And the red line, or ascending, and that they're parallel. And why are they parallel? It's the same orbit every time. The satellite is in a single plane, and it just makes a circle around that plane, within that plane, every orbit. The Earth is turning underneath it, and so every orbit you cross over a part of the Earth that's several hundred miles, maybe 1,000 kilometers to the west. Depends on your orbit period and how fast the Earth is turning underneath you. To me, that is just like the most confusing way to look at an orbit. So, okay, there's a couple of other vocabulary points that people talk about. I've got in slide 40 and 41 and 42 a bunch of really pretty pictures from STK of the Lagrange points. The Lagrange points start off being super simple. You can think about, a point between the Earth and the Sun where the gravities are the same. You have to be it's 1,000,000 kilometers from the Earth toward the Sun. It's unstable. That's called the first Lagrange point. That's the obvious one. Okay, I get that. The satellite is trapped between the Earth and the Sun. Therefore, it doesn't have to be in orbit around anything, right? It's not in orbit around the Sun. It's not in orbit around the Earth. It's just trapped at a particular spot between the Earth and Sun where the gravities are equal, and it's going to just sit there. It's unstable because if it happens to fall a little bit one way or the other, it'll just fall directly into the Sun or fall directly into the Earth. In that sense, it's unstable. So there's various tricks that we use to keep satellites exactly at the first Lagrange point. And there's a Lagrange point between the Earth and the Moon. And the confusing part is that there are many other Lagrange points. Any point where the gravities are equal is a Lagrange point, even if they're equal in the same direction. So at L2, because the Earth's gravity drops off much faster than the Sun, so once you start going away from the Sun, you reach a point where the Earth's gravity has gotten so small that it's equal to the gravity of the Sun. So that's doubly unstable because it's not stable at all. Then you can imagine like the L4 and L5, which are more vector sums of the Earth and Sun. And then there's even an L3. So there are a lot of Lagrange points, right? The only one that we've actually ever flown at is L1. It's very useful because you are on a line between the Sun and the Earth 1,000,000 kilometers from the Earth. So if you want to look for solar storms of particles that are going to hit the Earth, that's where you want to be because they don't go at the speed of light. So if you detect them on the satellite, you send a radio signal saying, hey, there's a walloping number of particles going by me right now, and here's their velocity, therefore here's how long it's going to take them to transition the 1,000,000 kilometers. You can prepare yourself on the ground for those, for that advancing particle field. Okay, so there's a lot of stuff in here in the slides for low thrust maneuvers and all that sort of thing, but we're not trying to do an exhaustive course on orbitals. I just wanted to, get you a few basic facts, and I'm fairly proud of the fact that I did that in 33 minutes. And I hope it wasn't too confusing, quick ride through it. Maybe you picked up something from what I was saying. On the last slide, there are a lot of very confusing terms used in the orbital world. And my defense of that, not that I invented any of those terms, not that I like them, and not that they're really falling off. I'm not an orbit mechanics guy. I'm like a guy who can read the book, but I couldn't write the book. So the way I excuse those in my own mind is every field. If you're a medical doctor, you know all kinds of Latin words for every crazy part of the body or element of the blood, and those are not words of the normal English language. If you're a lawyer, you know a lot of legal words about torts and all that kind of stuff. Or, you're a lawmaker. We all know that every field has its crazy, peculiar vocabulary. And so does orbital mechanics. So what I would say to you, here's a list of some of them. These are the ones you hear all the time, the right ascending node. The right ascending node is where the satellite crosses the equator on its way up, ascending toward the north, right? And relative to what? Relative to that line that goes from the Earth to the Sun at the spring equinox. And then, the true anomaly. I mean, these words are very, I don't know if they come from, the time of Kepler or what, But the true anomaly is not an anomaly at all. It's the angle that you've made. If you think of the orbit as being 360 degrees to go around the orbit, pick where the perigee is and tell me how many degrees you've gone from the perigee. That's the true anomaly. The inclination is the angle of the plane of the orbit compared with the equator of the Earth. So if you're in a 90-degree orbit, you're going over the poles. You can be in a 180-degree orbit. That would be an equatorial orbit going in the wrong direction. Instead of we always launch going from west to east because the Earth is rotating from west to east and fairly fast, several hundred miles per hour, like 600 miles per hour or something like that. And therefore, if you launch toward the east, you're basically getting a boost of 600 miles an hour, So that's which is 1,200, which is 300 meters per second, which is, an important part of your energy budget. If you live in Israel and you want to launch rockets and you've got countries that hate you to the east, they're going to be very mad at you if you launch over them, particularly if something goes wrong or particularly if you have to drop a rocket stage on their territory. So Israel launches to the west, and they put their satellites in orbit numbers of inclination that are more than 90 degrees, so they can launch over the Mediterranean, straight over, the Strait of Gibraltar, which is maybe a fine point in the law to say they haven't crossed over anybody's sovereign territory. But it's a big deal in the launch business, trying to find. That's why this launch company is starting up in Maine, because you can launch from Maine. In certain directions, you won't go over Canada. In other directions, you will. And in certain directions, you also won't go over like Kitty Hawk or Long Island. So they have a narrow range of angles that they can launch into that are basically toward the east, which is a good thing. And the real hot real estate in launching is to be at the equator with nothing to your east. And the reason I spent so long in Australia was in part that they were trying to establish a launch site on the north coast of Australia, which is only, as I remember, at 10 or 11 degrees from the equator, and where it sticks up the most from the main body of the continent. You could launch straight east, except for maybe Vanuatu. And I guess they were going to work the politics with Vanuatu, or you make a slight dogleg or whatever that is. And that's why Kourou, French Guiana, is so important. It's virtually on the equator, and there's nothing to the east. It's an excellent place to launch into equatorial orbit and eventually get to geosynchronous. So, okay, there's all these words. My other piece of advice for you about all these words is to read them. Not that you'll remember them. Every single one of them pops up very nicely on Wikipedia. So when you forget what sidereal is, that's the length, that's the star day, right? Normally it means referring to the stars, sidereal. But what we normally mean it to be is the sidereal day, which is the story of geosynchronous, that's 23 hours and, whatever it is, 50 minutes for the Earth to go around its own axis 360 degrees. And then it needs those extra 5, 10, 15 minutes to cover the extra degree so that it's pointing at the sun at the same angle, because we are moving around the sun. So anyway, I forget these words all the time. And what I would say is, when you see them, click it into Google and just read it very quickly. And after you've done that 3, 4, 5 times, you will remember what they are. It's super handy because people talk in these terms all the time. They want to know, what the ephemerids are. What the hell are the ephemerids? Those are what the rest of us call the orbit elements. Those are the numbers that describe the orbit, the 6 numbers. So, people talk about, the vernal equinox. What the hell is the vernal equinox? So, if you remember that one, it's the equal length of night and day, equal night, equal night and equal day. And there's two of them. And periapsis, apoapsis, we have perigee, which is the lowest point over the G. The geo is Earth, right? Like stationary over the Earth. So, but if you're not over the Earth, it isn't really correct to say perigee. You have to say periapsis if you're in orbit around who knows what, and apoapsis instead of the apogee. So then there's a big discussion in the whole, especially in the Hispanic world, about whether you can land on Mars. And finish off a discussion of terms, of vocabulary. I buy into the theory that you can definitely land on Mars. Land is not Earth. Land is just the surface, the solid surface of anything. Everything's got land. I mean, you could say the moon has real estate, right? It does have real estate. We could divide it up and build houses on it, and it would be land. I own land on the moon. So I don't see any particular problem with saying I'm landing on the moon. I do have a problem with saying I'm at the perigee around the moon, because perigee specifically refers to the Earth. But, I think landing is fine. I don't know why people get all excited about landing. So, you're not going to say mooning or Marsing. You're landing. You're landing unless you're, I guess you could be not landing if you're landing in the ocean. That wouldn't be landing. But nobody makes a big deal out of that. So, I think airplanes land, but they could just as easily land any place. So anyway, I guess I'm going to leave you with that slide. It's number 52. It's the last slide in the stack. I kind of feel like I have to apologize for rushing through it. On the other hand, I don't. I mean, it wasn't that we want to take a course in orbitology, but at least just to bump into the terms and see a couple of the problems, and so that you know what sun synchronous is, and you know what geosynchronous is, and you know what low Earth orbit is, and you know what an inclination angle is. I guess I should say one other number that is not in the orbit elements, which is something everybody calls the beta angle. And you'll always hear people talking about the beta angle. What is the beta angle? Anyway, the beta angle is the angle between the plane of the orbit and the plane of that, and how, well, let's put it this way. How much would you have to rotate that plane for it to point at the sun? Okay, that would be the beta angle. So if the orbit is beta angle 0, the plane is lined up with the vector to the sun. If you're at beta angle 90, you're perpendicular. What difference does that make? If you're perpendicular to the sun, you're kind of like in a sun synchronous orbit. You're going to get a lot more sun on your satellite. So in fact, satellites see a lot more sun when they're at high beta angles, and they see less sun when they're in low beta angles because they're hidden behind the Earth more. So we see that on our own satellites, and we'll definitely see it on this satellite, except we don't care because we didn't have solar panels. But if we happen to last 6 months, and if we happen to have thermocouples on the satellite, you would see that at certain times of the year, the satellite is hotter. Satellites experience seasons because when their beta angle is very low, they're spending 40% of their life behind the Earth in shadow. When their beta angle is high and you're in a polar orbit like we're in, you're very seldom shadowed, and you're going to get a lot warmer because your time period in which you can start to cool off is very, very limited. And that can actually be a problem. It's very stressing for the satellite designers. If you're going to be in orbit, a polar orbit for a year, you're going to go through summertime and wintertime. And it's stressing just for normal people like Equisat with solar panels because their amount of time in the sun. So as Equisat solar panels started to wear out from radiation probably, and the batteries started to wear out from so many cycles were on them, what we found was we very rarely contacted it when it was at a low beta angle because it didn't have enough time to charge its batteries. So anyway, beta angle, you hear beta angle all the time. It's not part of the basic orbit elements. It's part of the orbit descriptions that you'll get out of STK or any other orbit modeling software. So, okay, thanks for listening. And I'll do one more, quick broadcast for you on reliability. I hope this was in some way helpful. Bye-bye.